last thing I was trying to say with this problem is I know it looks really intense, I know it looks scary. Really what you care about is this stuff over here. I mean, this was if there's no rotational inertia for the pulley, this is if there is. It looks really scary, but didn't two body systems look scary the first time you did them? Okay? And you guys got to the point where they were a walk in the park. They're easy to deal with. Okay? Maybe you got to remember, maybe you got to review that a little bit, but you got to the point where this was easy. And you got to the point where no matter how it was set up, it was always kind of the same thing. Okay? There's not too many variations they can throw at you. This is kind of similar. Once you get to this step, once you got to take a little while to digest this, there's not a lot of variations. Okay? You're still doing net force equations. You have to throw a net torque equation in, and you're combining the equations. You might have to use this. That's really it. Okay? On the homework, you get to practice that a bunch of times, I believe. Okay? I don't exactly remember how many times you get to practice, but we're also going to practice one more time in the tutorial. And I apologize, it looks like we're going to go 5 videos. Sorry. Okay? It is what it is. The last topic on these notes is something that has shown up like once on an AP test, but I do want to discuss it because it has an application to engineering and everyday, I guess not everyday life, but things that you might see in the real world, and that is gearing. Okay? There's one homework question about this. So when I saw it, I was kind of like, well, I don't know how to deal with this, so I better make sure I talk about it. Here's the example we're going to do for gearing. I guess I can zoom in. No, that's too far. Okay, there we go. Gearing. So let's say you have this example. You have 2 discs, have a chain looped about them. And these discs have the same mass, but they are slightly different sizes. By slightly different, I mean one is twice as big a radius as the other. Hope you know I'm approximating here. That is not a good circle. I will try again. That's slightly less egg-shaped. Whatever. One has a radius of r, the other has a radius of 2r. They have a belt or a chain wrapped around them like so. There we go. Okay. Now, you might be asked, what is the ratio of their angular speeds? That might be something you're asked. You might be asked, in terms of one angular speed, what is the other? Or in terms of one angular acceleration, what is the other? Here's the key thing here. Okay, this is a belt. The belt does not slip or stick. It stays right on these, and then obviously it comes off and it goes to the next one. The belt guarantees, if it doesn't slip or stick or slide on these, what it guarantees is that the linear speed at the edges must be the same. Think about what it would mean if it wasn't. If the linear speed, if this edge right here was moving faster than this edge, you would get the chain kind of bunching up. Okay? Or if this was moving faster than this, you'd get the chain kind of slipping under the belt or under the chain. As long as there's no slipping or sticking, that's not going to happen. So what we know is that the linear speed, v, of the chain must be equal at every point. Okay? So that's important. Let's take a step away from that for a second. Let's talk about the rotational inertia of these disks. Okay? We actually just got done saying that the equation for rotational inertia of a disk, which you have in the last problem, is 1/2 mr². So, for the first disk with radius r, our rotational inertia is just 1/2 mr². What about for the disk with a radius of 2r? What's the rotational inertia there? Well, we said the masses are the same, so we have 1/2 m. R, for the bigger one, is twice as big. We end up with, let's see, 2r² is 4r² times 1/2, let's see, that would be 2mr². Or another way of writing that would be this. Don't get fooled by the coefficients. It is not twice as big as this. Look at the coefficients. 2 1/2. The rotational inertia of the second disk is 4 times the rotational inertia of the first disk. Okay, it's 4 times as big. I want to talk about that because I think that shows up right on a homework problem. Let's go back to talking about the linear speed of the belt. It has to be the same at each point. Otherwise you get slipping and sticking of the belt or the chain. VR equals V2R. Okay? The linear speed at the outer edge of these disks must be the same. Well, thankfully for us, we know that V is equal to the radius times the angular speed. And that's the case for both of these. We know this radius is simply r. We know this is 2r. We can cancel out the r's. And we get this nice relationship. The angular speed of the second of the bigger disk is half the angular speed of the first disk. The first disk will make rotations quicker. And that kind of makes sense. Okay? If they're going to have the same angular speed, or linear speed, that means that the belt covers the same distance in the same amount of time. This one is bigger. Okay? It doesn't have to rotate that quickly for the belt to cover a big distance, a big linear distance. This one, on the other hand, has to rotate very quickly, since it's smaller, for the belt to cover the same distance. So it kind of makes sense that the bigger one has a smaller angular speed. And you know what? If they ask about angular acceleration, it's pretty much the same result. You can use the same logic. Same result for alpha. You get that alpha of the little disk, you cut it in half, and that is the angular acceleration, if there is any, of the bigger one. Okay? Gearing, I highly doubt it will come up, but it has come up in the past before. I haven't seen it come up yet on the new test, but I want you to be prepared, so that is why we talked about it. Okay? So, there's about 40 or 50 minutes on rotational kinematics and dynamics. We're going to go to one tutorial question. The first part of which is fairly easy. It's going to be another problem where we are translating, we're going from what we used to do with these types of problems to what needs to be done now if we're going to take rotational inertia into account. We're going to take into account that it takes, some effort to make these objects rotate. So, okay, that one's done. Over here. Alright, so like I said, the first part of this is going to be fairly straightforward. Let's say you are a building company. Supplies need to be moved up to the top floor of a high-rise building during a construction project, eliciting debate about the best way to do this. Eventually, the workers decide. You guys know I like to make up these ridiculous situations. Workers decide to build a very simple pulley system consisting of the supplies, which have a mass of little m, a massless rope attached to them going upward over a pulley, a second mass, capital M, attached to the other side of the rope. So draw a free body. So here's a picture of what's going on. They're saying, how do we get the stuff up to the top? Here's little m. Here's our pulley. Here's big M. Okay? Basically saying, make this really big, allow it to move down, hoist the supplies up to the top. Free body diagram for the system. This should be extremely straightforward. We're going to go under the assumption right now that the pulley doesn't tell us the pulley has mass. Let's assume the simplest possible case. Okay? For little m, T up, F, G, M down. Here's our axis. For the big mass, still have T up. And again, because we're assuming right now the pulley has no mass, we can say the tension's the same in both cases. Whoop-de-doo for us. If the little mass is being hoisted upward and we're calling that positive, the big mass moving downwards has to be positive for the big mass, okay? There's a free body diagram of the system. We will solve that in just a second. That should be about as basic as it gets for you guys at this point, okay? This next question, what condition is necessary for M so that the supplies are guaranteed to actually make it up to the top of the building? Justify your answer without using equations. This is where, sometimes we go off the rails. You guys start to answer, and your answers start going all over the place, okay? Well, we need to get M to the top, and we need it to be guaranteed that M is going to get there, all right? If we're guaranteeing M has to get there, that means it can't start slowing down before the top. Well, if it can't slow down, that means it has to either have no acceleration as it's going up, or it has to have positive acceleration as it's going up. So I guess what I'm saying here is that in order to lift M so that it is guaranteed to reach the top. Well, we just said it can't have a downward acceleration. Either it has to have no acceleration or an upwards acceleration. If you think back to our free body diagrams, that means that the tension acting on the little m has to be either equal to the force of gravity on little m or greater than little m. So we should say the tension on M must be equal to or greater than the force of gravity on little m. Okay? If it's equal to, it won't have any acceleration that goes up. As if it's greater than, it'll have upwards acceleration, positive acceleration as it goes up. Okay, so tension. Okay, sorry, I'm just trying to read what I was saying here. Okay. So tension on M must be equal to or greater than the force of gravity on M. Since we are assuming, for right now, that tension is the same at all points in the rope, the tension on little m must be the same as the tension on big M. Okay, that's our normal assumption that we make when we ignore the rotational inertia of the pulley, which is what we're doing for right now. Same as the tension on big M. Okay. Okay, this means that, well, let's see, if those tensions are the same, if little m is either moving at a constant velocity or accelerating upward, big M must either be moving at a constant velocity or accelerating downward. Well, in order to achieve this, if big M is either moving at a constant velocity, that would mean that the tension is equal to the force of gravity on big M, or if big M is accelerating downward, that means the force of gravity is bigger than the tension. The force of gravity on big M is bigger than the tension on big M. So in order to achieve this, the force of gravity on M must be equal to or bigger than the tension on M. And if we go back, we could see that the tension on big M is the same as the tension on little m. The tension on little m had to be bigger or equal to the force of gravity on M. So what this allows us to conclude, and you're probably like, well, duh. What this allows us to finally conclude, without using any equations, is that, let's see, force of gravity on M, big M, must be equal to, which leads to the conclusion that since the force of gravity on big M must be bigger than or equal to the force of gravity on little m. Therefore, big M must be equal to or greater than M. So I think my writing got pretty bad at the end, right there. Not my handwriting, like the actual justification writing. I think it got pretty sloppy there. I was trying to rush a little bit. If you read this through a couple times, maybe you write this out in symbols. I said, the question says justify your answer without using equations. That doesn't mean like you can't on like scrap paper like scribble it out somewhere else and then write a paragraph. Okay, that's fine. But read this to yourself a couple times. Okay, it should make sense after you read it once or twice through. I know it's kind of got a little sloppy at the end, but in order to make sure that this makes it to the top, big M must be bigger than little m. It absolutely has to be. Okay. Here's what we're going to do. Let's assume that big M is equal to 3 times